This is a part 2 of the final video 4, and this week our work focuses on the design of a hardware-assisted deep packet inspection system. We conducted an in-depth study of 2 research papers and implemented key parts of their proposed methods, including feature extraction, neural network training, and hardware-aware model preparation. Cause in high-speed networks, traditional software-based intrusion detection systems like SNOS often suffer from performance bottlenecks, specifically under 10 gigabits per second traffic. They may experience high processing latency, overloaded system resources, and even missed detections. To address this, our project aims to build a lightweight artificial neural network intrusion detection front and deploy it on the NetFPGA platform, capable of real-time packet classification with low latency and efficient resource usage and high detection accuracy. The first paper we read is this. Slot offloader, a reconfigurable hardware NIDS filter. This paper proposes moving SNOS front-end filtering functionality to FPGA hardware to reduce SNOS computational burden, and the core architecture includes the active filter, which quickly drops non-safe flows based on 5 turbo fields, and there is a header classifier which implements SNOS header-only rules using combinational logic, and the two-level Bloom filter is used to efficiently match payload strings with low false positive rates, and the last one is control center, which supports remote rule updates and dynamic job strategies. In this paper, the experiment show that with just 48 block lengths, the system can filter out over 87% of benign traffic, reducing SNOS workload to only 1.3 gigabits per second from the original 10 gigabits per second, achieving high throughput and low latency filtering. Cause we want to replace all the Bloom filters functionality with the artificial neural network, so we read the second paper. Which is the applying hardware-based machine learning to signature-based network intrusion detection. This paper takes a different approach, leveraging a commercial CM1K neural network chip to implement a lightweight intrusion detection system called C-Light. Rather than relying on pattern signatures, it classifies packets as benign and malicious using a LAN model. And the key innovation lies in the feature extraction process using n-gram and the hash to construct the feature vector. And the process of the feature vector construction is the first one is generate the n-gram. Each package payload is split into a fixed size n-byte segments using a sliding window, typically n equals 5. This captures local byte patterns, and then is hashing. Each n-gram is passed through murmur hash, producing an 8-bit value, representing a histogram bin index. And the formation of histogram is a 258 dimensional feature vector, where each bin counts the number of occurrences of the corresponding hash value. And the last step is to combining the histogram with the header. These 256 payload features are combined with 5 hash factorial fields to form a 256 dimensional input vector. And there are 4 main advantages of this method. First is protocol agnostic, applicable to USB, TCP, UDP, Bluetooth, Zigbee, etc. And the second is compact representation with low dimensional and sparse, suitable for hardware. And the third is generalizable, which learns structural patterns instead of fixed byte sequences. And fourth is efficient for parallel hardware. The symbol counters can form histogram logic, and in this paper, even under highly imbalanced datasets, the model achieved over 99.8% accuracy in real packet traces, demonstrating strong potential for low power real-time classification in edge environments. And then is the process of implementation and the feature pipeline reproduction. Cause we use the TCP dump to capture the real network traffic, but we found that the malicious parts of the real network is account for a very low parts, so we incorporated the CIC IDS 2017 data set with our real network traffic.pcap. This dataset have all the features we need, and it is the intrusion dataset. And then here are 2 scripts as well as the Python file for training. This first script is used to extract the 5 tuple as well as the payload of the real network packet. And then the second script is used to combine the slot log with the extracted features data set to form the labeled features data set. It is The main function of this is used to label the packet with malicious or normal. And here is the training file. We built a lightweight ANN which is 256 inputs and 3 hidden neurons and 1 logic output. We use the BC with logic loss plus add-on optimizer. After training, we exploited the weights and biases and quantized them into innate format to save the corresponding scale factors and stored as TXT files for hardware compatibility. So that's all the works we done, and our next week's steps include converting the ANN inference into Verilog RTL and integrating with NetFPGA's router module. That's all. Thank you.